When calculating voltage drop for 200 amp underground service using underground service entrance or use cable, it's important to understand which ampacity values to use. While table 310.16 determines the allowable ampacity at 75 degrees Celsius for the cable, for voltage drop calculations, you will use the 200 amp ampacity as specified in section 310.15. B816. The formula for voltage drop is as follows: voltage drop equals 2 times distance times ampacity times resistance divided by voltage. Let's break down each parameter in detail. Firstly, distance refers to the total length of the underground service entrance cable run, measured in feet. This is the one-way distance of the conductor. Secondly, ampacity represents the current flowing through the conductor, which in your case is 200 amps. Thirdly, resistance is the resistance of the underground service entrance cable per 1000 feet, and this value can be obtained from table 310.16 in the National Electrical Code, or NEC. It is measured in ohms per 1000 feet. Finally, voltage is the supply voltage for your service, which is typically 240 volts for a 200 amp service. To illustrate with an example, let's assume you have a 100-foot underground service entrance cable run, and the resistance of the cable from table 310.16 is 0.180 ohms per 1000 feet. Plugging these values into the formula, we get voltage drop equals 2 times 100 feet times 200 amps times 0.180 ohms per 1000 feet, all divided by 240 volts. Simplifying the calculation, we have voltage drop equals 7200 divided by 240, which equals 3 volts. Therefore, in this example, the voltage drop for your 200 amp underground service using underground service entrance cable is 3 volts. It is important to note that you should use a voltage drop calculator that specifically accounts for the 200 amp ampacity allowed by section 310.15. B16 for underground services. Using other ampacity values will underestimate the actual voltage drop. Now let's delve deeper into the concepts and the code sections involved. Firstly, understanding ampacity and its determination. The ampacity of a conductor is its current carrying capacity, expressed in amps. It is the maximum current a conductor can carry continuously under specific conditions of use without exceeding its temperature rating. Article 310 of the National Electrical Code provides guidelines for determining ampacity. Table 310.16, as mentioned earlier, is a key reference for ampacities of insulated conductors rated up to 2000 volts, with temperature ratings of 60 degrees Celsius to 90 degrees Celsius. These ampacities are based on specific installation conditions, such as the number of conductors in a raceway or cable and the ambient temperature. Secondly, use cable and its applications. Underground service entrance or use cable is specifically designed for direct burial in the earth or for installation in underground raceways. It is sunlight resistant and suitable for wet locations. The insulation of use cable is typically a thermoset compound like cross-linked polyethylene or XLPE, which provides excellent electrical and mechanical properties. When using use cable for underground services, you must ensure that it is installed in accordance with Article 300 and Article 310 of the NEC, as well as any local codes or regulations. Thirdly, Section 310.15 and ampacity correction factors. Section 310.15 of the NEC provides the general requirements for determining conductor ampacity. It covers factors such as ambient temperature correction, adjustment factors for the number of conductors in a raceway or cable, and terminal temperature limitations. The ampacities listed in Table 310.16 are based on an ambient temperature of 30 degrees Celsius or 86 degrees Fahrenheit. If the ambient temperature is higher than 30 degrees Celsius, you must apply a correction factor to reduce the allowable ampacity of the conductor. These correction factors are provided in tables such as Table 310.15, B1, and Table 310.15, B2. Similarly, if there are more than 3 current-carrying conductors in a raceway or cable, you must apply adjustment factors to reduce the allowable ampacity of each conductor. These adjustment factors are provided in Table 310.15. B3. The purpose of these correction and adjustment factors is to prevent conductors from overheating and potentially causing a fire or equipment damage. Fourthly, voltage drop considerations. Voltage drop is the decrease in voltage along a conductor due to its impedance, which includes resistance and reactance. Excessive voltage drop can cause lights to dim, motors to run slowly, and other equipment to malfunction. Section 210.19. 8.1 of the NEC provides guidelines for voltage drop in branch circuits. It recommends that the voltage drop should not exceed 3% for branch circuits and 5% for feeders, for a total of 5% voltage drop from the source to the farthest point of utilization. Section 215.2. A3 provides similar guidelines for voltage drop in feeders. To calculate voltage drop, you can use the formula we discussed earlier or an online voltage drop calculator. The key parameters are the length of the conductor, the current flowing through the conductor, the resistance of the conductor, and the voltage of the circuit. It is important to use accurate values for these parameters to obtain reliable voltage drop calculations. Fifthly, resistance values in Table 8. Table 8 in Chapter 9 of the NEC provides the resistance and reactance values for various types of conductors. These values are typically expressed in ohms per 1,000 feet. When calculating voltage drop, it is important to use the appropriate resistance value for the specific type and size of conductor you are using. For example, the resistance of a copper conductor is different from that of an aluminum conductor. Similarly, the resistance of a larger conductor is lower than that of a smaller conductor. Table 8 also provides the alternating current resistance and reactance values for conductors in raceways. These values take into account the effects of skin effect and proximity effect, which can increase the resistance of conductors at higher frequencies. Sixthly, calculating voltage drop with reactance in alternating current, or AC, circuits. Voltage drop is affected not only by resistance but also by reactance. Reactance is the opposition to the flow of alternating current caused by inductance and capacitance in the circuit. Inductive reactance is caused by the magnetic field created by the current flowing through a conductor, while capacitive reactance is caused by the electric field created by the voltage across a capacitor. The total impedance of a conductor is the vector sum of its resistance and reactance. The voltage drop in an AC circuit can be calculated using the following formula: voltage drop equals current times impedance. The impedance can be calculated using the formula impedance equals the square root of resistance squared plus reactance squared. When calculating voltage drop in non-AC circuits, it is important to take reactance into account. This is especially true for large conductors and high current circuits. Seventhly, importance of accurate calculations. Accurate voltage drop calculations are crucial for ensuring the proper performance and safety of electrical systems. Underestimating voltage drop can lead to equipment malfunction, overheating, and even fire hazards. Overestimating voltage drop can result in unnecessary costs due to the use of larger conductors than necessary. By carefully considering the factors that affect voltage drop and using accurate calculation methods, you can design electrical systems that meet the requirements of the NEC and provide reliable and efficient power to your loads. Remember to always consult the latest edition of the National Electrical Code and any local codes or regulations before designing or installing your electrical systems. It's also recommended to consult with a qualified electrical engineer or electrician if you have any questions or concerns about voltage drop calculations or other electrical design issues. The information provided here is for general guidance only and should not be considered a substitute for professional advice.